week. So without any further ado, please give a warm Shmoocon welcome to Tim, who will be talking about, or excuse me, Ian, who will be talking about certificate transparency.
Thank you very much. And it sounds like you're all in the right room because you failed the trivia. So a little bit about myself. I'm a senior product engineer at a large cloud company working to keep the cloud secure by day. And at night, I would like to work on security research. Sometimes that research involves... Sure, I'll speak a little louder. Sometimes that research turns into stuff I present at conferences, and sometimes I learn a lot of things that fail and go nowhere. If you're interested in hearing about these types of ramblings, you can follow me on Twitter or my blog. But that's enough about me. So first, I'm going to start off with a little bit of an overview of how SSL certificates work so you can understand the rest. So there are SSL certificates. They're issued signed by CAs. They're usually limited by the domain names they're valid for, dates, or some certificates have the ability to sign other certificates, which is a CA certificate. And as part of the SSL handshake, when the client sends its SSL client hello to the server, the server sends its hello back, which the client receives. The client does verification of this. I'm not going to go into details of how that works. But if the client says that this checks out, it will resume the SSL handshake and a secure connection established to the server. So one day I was browsing a popular webcomic, which you can't read that text at all on these projectors, xkc.com, and looking at the SSL certificate. And in there you see, on the alt names, you see things for goodeggs.com and grindr.com and some other hosts as well. So I was trying to figure out what Randall Munroe, the creator of XKC, would have to do with grindr.com. And the reason for this is that XKC is using a CDN, and the CDN makes one SSL certificate that's shared among all of their customers, resulting in this. And this is basically due to overloading certificate alternative names, where you have all the hosts on one certificate. Some examples is like, say, EFF.org and www.ef.org. You can also have wildcards. It's a very, very common practice on SSL certificates these days. So I'll talk a tiny bit now about obtaining certificate. Is the job of the certificate transparency to verify who you are when you request a certificate. Depending on the type of certificate that you're requesting, they might do just to verify that you own the domain name or can receive an email from the WHOIS record, or actually verify your business or your ID or anything, or if you're going for an extended validation certificate. And of course, if you want, you can get basic domain name SSL certificates for free from Let's Encrypt. I highly encourage everyone to use them. It's a great free service. So now a little bit about what happens if a certificate authority misbehaves. And there are some recent examples of this. So in March of 2011, Komodo, at the time popular reseller of certificates, was compromised. And 9 certificates for 7 different domain names were issued, including Google, Live, which is Microsoft, Yahoo, Mozilla, and Skype, and some others. And these include subdomains of them as well, wildcards, and an intermediate CA certificate. So you can create more certificates for these domain names with the certificates that was leaked. Komodo immediately revoked the certificates that were issued, basically thwarting the attack. Worst case of this happened a little later is DigiNotar, which was an Illinois-based CA primarily used by the Dutch government. It was breached in June 2011, but it wasn't detected until July, so a whole month of being compromised. And the reason why they compromised is they lacked basic security safeguards such as strong passwords, antivirus, software patches, etc. So an attacker was able to get in using these insecurities and basically issue over 500 certificates for, again, very common top websites. And of course, when DigiNotar found out, they decided to try to cover it up and not tell anyone about it. It wasn't actually discovered until some users were looking at certificates and realized that these are not the actual certificates that you should be expecting from those organizations, aka they are being found being used in the wild by the attacker. And basically overnight, all browsers blacklisted the CA because they covered up being breached, and they're unable to cover from that. Basically, they're no more income, and they filed for bankruptcy shortly after. And a more recent example of this is Symantec, also known as Thwate, VeriSign, Equifax, GeoTrust, Rapid SSL. They resell under various different names. And when they do these resell, they trust these other organizations to sign certificates on their behalf. And some of these other organizations didn't have very good security practices. Symantec didn't actually verify that they were doing what they were supposed to be doing. So in 2015, Symantec issued an extended validation certificate for Google.com that Google did not authorize. It was someone impersonating them. And this was discovered in the certificate transparency logs, which is what we're going to be getting into in a little bit. Also at the same time from Symantec, they found 164 other certificates for 76 domains, and over 2,000 certificates were issued by them for domain names that never even existed. So someone was going in there and just seeing what they could do. And then more recently, in 2017, the 108 more unverified certs were found. And basically, Symantec had a problem where If you request a certificate for a domain that didn't exist, it would fail open, issue it to you, and then, of course, you can get the domain name afterwards. That has also been fixed. So now getting into certificate transparency. So certificate of transparency was basically standardized in RFC 6962, and the goal was to provide an open auditing monitoring system that lets any domain owner or certificate authority determine whether or not the certificates have been mistakenly issued or maliciously used. So it's a public log, or it specifies there are public logs that CAs submit all their certificates to, and anyone can audit these logs, whether it's you as a user, a domain owner, another CA, a company, anyone. And these logs are usually updated in near real time, so you can get notification of a new certificate being issued within an hour, usually much less. So going a little bit of the timeline of how this happened. So we had our initial breach in 2011, and then a few in 2013. And in 2013, Google started the RFC to create certificate transparency to solve this problem. In September 2013, DigiCert was the first CA to start implementing this and logging all of their certificates publicly. And in 2015, a few years later, Chrome requires that all your certificates for EV certs are in the certificate transparency logs, aka a CA needs to show that the certificate was publicly auditable for EV certs. Of course, in 2016, we had the semantic issue I just mentioned, and in April 2018, Chrome will require certificate transparency for all certificates, not just EV. So this is a little bit of how this works. So there are three different components. We have the public logs, we have the auditors, and monitors. And all three work together to basically audit each other and make sure that no one misbehaves. So going into a little bit of detail of that. So first off are the logs. These are basically stored certificate logs. These are that append only Merkle tree hashes, and anyone can audit these. They issue, when a CA submits a certificate to a certificate transparency log, they receive back a SCT, or signed certificate timestamp. And that basically, when the browser receives that in the certificate, it allows them to verify that the certificate is actually in that log. And that's basically how a user or an auditor, which we're going to get to in a little bit, can verify this. Logs also should refuse to publish certificates that don't have a valid certificate chain, and it is important that the logs are independent from certificate authorities or SSL clients. Otherwise, there could be collusion, and you cannot trust the system. And of course, anytime you need to present the log for an audit. So the next part is the monitors. The monitors are sometimes implemented as certificate authorities, but they don't always need to be. And these act like credit reporting agents looking for suspicious certificates being logged. This could be illegitimate or unauthorized certificates, unusual certificate extensions, such as logging a CA certificate for a domain name, or certificate same permissions, which could be the same thing as that. And their job is to verify that all certificates that are visible actually appear in the log. So, okay, if you are a client or a monitor, or you're looking at SSL certificates, you receive a certificate with an SCT, verifying that if you actually present the SCT to the log, you actually get the same certificate back, making sure that there's no funny business going on there. And these are often implemented certificate authorities, but they don't need to be. The last chunk, or last item here, is the certificate auditors. These are the clients to the log servers usually. These check the logs and make sure they're behaving correctly, make sure there's no inconsistency, make sure you're not skipping serial numbers or not missing certificates or don't have extra certificates in there that you can't actually pull out. The signatures and logs data structure, the signatures and log data structure is a Merkle hash tree. Let's get into in a bit, but that basically is a cryptographically secure way of showing that you cannot modify the log after it exists. And these may be implemented in a browser's TLS client. Chrome, as of version 61, has already started doing this. Other browsers as well soon too. But it does not need to be implemented at the auditor. So, like I said, the monitors and auditors can also speak to each other if they're not implemented at the CA or the browser too. They can be independent, and anyone can run either three of these components on their own if they need to. So the certificate transparency log is really just a Merkle tree log. It's just a hash tree where each new block of certificates is added, and you have a leaf hash over here. Not sure if you guys can see my mouse here, where it just contains a hash, and then you have a hash of the other nodes up to the root. And so when you add chunks, which are done in blocks, like say every hour, every 5 minutes or so, depending on how many certificates you have, you'll create a new tree and just make a hash of the two new roots, and that's your new root of the new tree. And so you can never tamper anything in the back because it'll invalidate the hash. So it's append only. These logs are going to get larger and larger and larger. I think as of around a month ago, the most certificate transparency logs are about 500 gigabytes in size, with about 500 million different certificates at this time. And if this all sounds Merkle tree logs sound familiar, that's because this is blockchain technology, not just using cryptocurrencies. So a side effect of this is that every certificate being logged, which includes all the domain names it's good for, is being logged publicly. Everyone can see the domain names being logged. Additionally, when your browser checks for valid certificates, it will be sending the SCT, the certificate transparency signature, to the logs for verification. And this leaks what domain names you are browsing to the log as well. This is a current issue. There's no current accepted solution to this. There's ongoing discussion, though. So the two main solutions to this at this time are to hash the domains or subdomain names when you're putting them in the logs. But this is still vulnerable to dictionary attack because you can enumerate all the hashes and see what domains are being issued by various CAs for what companies or what domain names users are visiting. Alternatively, you can use a wildcard. However, the downside of that, using wildcard domains, is you can only redact the leftmost label for a domain name. So in this example here, if you have something you want to redact secret.example.com, but you have another subdomain among that, you can only redact basically the first part, and the secret part still is going to be public. And assuming that either of these solutions are actually implemented, or let's say the hashing one, how can a monitor still verify? Like, okay, how can you check to make sure that none of your new domain names are being added to the log? You can do that if you only see hashes, and the answer is you'll look for the number of certificates that come up with the search of your hash. You won't know what domain names they're for, but as long as you never see number increase when you don't request a new certificate, then you're still secure. So tangentially related to certificate transparency is the Certification Authority Authorization DNS record. And this is a simple DNS record that is required as of September 2017 for all CAs to check your DNS records to see if you have this record. And it allows you to specify if a CA is allowed to issue domain names for your certificate. If this record does not exist, then it's basically fail open. Any CA can issue any certificate. If you do specify, say in this example on here, only Let's Encrypt is able to issue certificates for you, then if you say you request a certificate from Symantec and they see this record, it should fail. However, it should be noted that they only check at the time you request a certificate. So when looking at certificates, you might see that a certificate was issued by, in this example, for Symantec, but you may have not had this record at the time Symantec issued the cert. In that case, that cert's still valid. So it's only for at time of issuing. And you can limit stuff based off wildcard or subdomain names as well. And you can also specify instant object description exchange format, which basically means if a CA sees that it's not authorized to issue a certificate and it's being requested to add one, you can put a mail to link in there or a URL where it'll send an email or send a post request to this URL with the information about the violation of the port so you can figure out what went wrong. And that's a good way to kind of enable in a report-only mode so you can see if you want to implement this policy and actually enforce it. Additionally, is the expect CT HTTP header. And this is a new HTTP header that allows sites to tell browsers to expect certificate presented by a website in the log. It's basically a way you can tell current web browsers to enable certificate transparency validation in the client or the web browser before August 2018. So you can enable it now. It's currently implemented in Chrome 61 and Opera 648. Firefox is implementing support soon. And similar to the CA DNS record, you can set a report URI where browsers will report to you if there's a violation. This only supports URLs. You can't put mail to links in there. You can say how max age is how long to enforce or cache this policy. And enforce is optional. You could set it to enforce. It'll actually abort the connection if the certificate's not in the log. But if it's useful right now to leave it not enforced and have a report URI so you can see if you would basically be sent to your clients if enabled. So it's really useful for testing. So now I want to talk about some good certificate transparency tools. Google, Komodo, and Facebook have really good certificate transparency search engines. I can show you that in a little bit. So a little blurb here. If you sign up for the Facebook one, they'll send you Facebook notifications whenever a new domain name or new certificate is issued for a domain name you have, and it shows it right on Facebook. If you're into that sort of thing, it's kind of odd to get those notifications, but odd. So I'll show this right here. So for example, Google is a good search engine. You can't see that at all, but if you could, let's see here. Searching something like, say, Shmoocon.org, you'll see their CA and their SSL certificate right here where you can just see the details. It's good for 2 domains, etc. The CRTSH, in the interest of time, I'm not going to go going into too much into that. So I want to get into the tool I wrote. So wouldn't it be nice if you could find misconfigured certs to host discovery, do the domain name enumeration of all the certificates that are in the public and available, and create a trust graph for these certificates. So that's where the tool CertGraph comes in, which I wrote to do exactly this. So this works by using a modified breadth first search in parallel. So you give the root domain name of where you're interested in looking at, and it looks for it grabs certificates for that domain name, looks to all their alt names, gets all certificates for those, goes to all alt names, and keeps going until it creates a complete graph. And you can grab certs over HTTPS, SMTP, CRT search engine, or the Google Certificate Transparency search engine. So here's an example, just looking at what happens if you give it just EFF.org. So you can see this, yes. It shows you basically, you can see that their dev boxes, kittens, some other Atlas, some other cool stuff in there that you may not know is publicly available. You can also print out more detailed information like the hash of the certificates, whether or not these hosts are actually accessible over the internet. For example, this one here, this dev is not accessible over the internet, or at least didn't respond to an HTTP request. The rest you can all establish a connection to. And of course, you can visually graph these graphs too. So you can see here's the root node, EFF.org. It had this certificate, which is also good for these domain names. Oops. This certificate was also valid for it. This is just the prefix of the hash, which is good for these domain names. You can see how it kind of got further down into these dev environments from where their production is. So this is a graph that's kind of interesting. I like to point an example. When you get long tails like this, it could mean that something's a little bit more interesting here. So we started here at the domain name Salesforce.com and ended up down to Squarespace.com. And for those who don't know, Squarespace.com is another company that has nothing to do with Salesforce.com. Their certificates should not be linked in any way. So what happened here, Salesforce.com owned the domain name do.com at this time, and then sold it or let it expire. Somehow, Squarespace.com became to own that domain name. However, Salesforce, in their production web server, their certificate they were using was still good for do.com after they got rid of it or no longer owned the domain name. Okay, they didn't revoke the cert, renew it, or anything like that. And Squarespace didn't check to see if anyone already owned a cert for their domain name when they got it. So that's something to keep in mind here. Whenever you're getting a domain name, you should check certificate transparency logs to see if someone else had previously owned it and has a certificate for that domain name, because they can then potentially manipulate your users. So the solution to this is just basically revoke that certificate, in which case you get a much smaller, neater looking graph, which is what it should look like. And of course, this tool also comes with the web interface. It's just a single HTML page, doesn't need to run offline, lets you play at the graph and view everything. And this is what happens if you do a graph of something of a CDN, similar to the XKCD example I showed at the very beginning, where there are potentially thousands of domain names or certificates for a single host. It doesn't look too useful right now. So this is where you can get the code. It's open source. You can download here. You can use the web UI. I highly recommend the CRT search engine. Google's is also very good. One nice thing about this one, which is run by Komodo, it's a web UI in front of a Postgres database, and they let anyone connect to their Postgres database remotely over the internet. So, you can't write to it; it's read-only user, but you can run raw SQL queries along certificate transparency, and that's how my tool CertGraph works. And now I'd like to do some quick demo. So this is just the web interface. This is what it looks like for DFF.org. I want to now, so you guys see this? Yeah. Looking for say Shmoo.com, nothing too interesting there. I'm going to tell, that's just using HTTP connection. Driver. Oops. All right, so just, again, not too interesting, just looking for domains for Shmoo.com is only one. Now if I do CT dash, wait. If I tell it to include subdomain names, we get some interesting stuff here now. So why we're not on Mars yet, this is why we're not on Mars yet. I don't know what those things are. Kind of curious. Okay. I don't know what that is. But you find cool stuff like that. It's not a problem. You can also do certificate transparency also logs expired certificates as well. So again, it's a Merkle tree append-only hash. You can also get expired ones, which you get a few more things on there like IMAP. I guess they have an expired IMAP cert. But let's hear this. Actually, wait. Now let's try to graph that and see what that looks like. So you can just tell it to give a JSON output. One dot. That's just going to output a bunch of JSON. But if we want to graph that, see what that actually looks like in the UI. File upload, choose a file. Shmoocon. You can see, so we have this one domain name here has a lot of different certificates for it. I don't know, it's an odd thing here. We have this other stuff over here, some infrastructure stuff that's all linked together. The actual domain name, as you saw, shmoo.com is all by itself. It looks like they're just using wildcard certs. So for the purpose of this, since I can't enumerate subdomains wildcards, I just assume wildcard is its parent domain name. And then a bunch of other stuff clustered here together, lots of Mars things. I also want to show, so another cool example of this that you can do. So doing Shmoocon, since we're using the CRT-SH driver, it's just running raw SQL queries, you can actually enumerate entire TLDs. So say I wanted to look at every domain name that has a .mil domain name. I'm going to remove it, exclude that because that'll take forever. And since I'm running the raw SQL queries from CertGraph on my laptop right here, it is also dependent on the CON network. So this might take a second. Worked earlier. Well, while it's loading, I did run it earlier and save the result as JSON, so I can show you what that looks like. Upload. This is every .mil domain name and certificate that is in the certification transparency log. So there's a lot of them. And since the graph isn't too useful, I'm not sure if you guys can see this. Zoom in a little bit more. You can just scroll down and see all of these domain names. It's really cool if you just want to figure out what data is being leaked, or just get like a list of hosts for a TLD or a normal domain name. Really good for subdomain name enumeration. Also can view the certificates too. All here. And I think I'm about out of time, so I think that's it for here. If you have any questions, I can answer them outside. Thank you. What? It'll work on all of them. I just got